So, given a particular complex number, a plus bi, how do you find the trigonometric form? How do you find the r and the theta so that you can write r times the cosine of theta plus I times the sine of theta? Well, if you're working it out for yourself from the formulas, r is the square root of a squared plus b squared. And theta, well, start by taking the arctangent of b over a. But sometimes you have to do more than that. There are two complications you have to worry about. The first is that b over a would give you the same number if b and a are both positive, like if you're in quadrant 1, as it gives you when b and a are both negative, like you're in quadrant 3. So a positive divided by a positive and a negative divided by a negative both come out the same, and so they would give you the same angle if you just do arctangent of b over a. Same thing, it can't tell the difference between b being negative and a being positive, or b being positive or a being negative. So if you just do this, it might give you an angle that is in the wrong quadrant. And if that happens, you just have to add or subtract 180 degrees if you're working in degrees, or pi if you're working in radians, to get the angle in the correct quadrant. The other complication is that this formula won't work if a is 0. You have a division by 0 error. But in that case, if a, which is your real part, is 0, then you're talking about a pure imaginary complex number that is on the imaginary axis. And so the angle has to be either 90 degrees if it's straight up, or 270 degrees if it's straight down. So if a is 0 and b is positive, theta would be 90 degrees, or pi over 2 in radians. If a is 0 and b is negative, then you have to say that theta is 270 degrees, or 3 pi over 2 in radians. So that's if you're doing it yourself. But your calculator probably has a way of handling all the gory details and just doing the conversion for you. So different calculators have different ways of doing this, but the common scientific or the common graphing calculators have actually more than one method. So one method, if you're using something like a TI-84, goes like this. Remember that we need two numbers, the r and the theta. To get the r, push the math button, use the right arrow to select CPX, which of course stands for complex. And now go down and select ABS from the menu. That stands for absolute value. We're asking for the absolute value of a complex number. When I hit enter, now it's going to let me type in the complex number that I want the absolute value, or the r, of. The example we were looking at was 5 minus 7i, so I'm going to put that in as 5 minus 7i. And I got the I by pushing the second button and then the decimal point button that has a little blue I above it. So now when I hit enter, it tells me that the absolute value of 5 minus 7i is 8.6, 0.2325267. So that's r. What about theta? Okay, push the math button, go to CPX, and this time select angle. And again, put in the complex number that you're converting, 5 minus 7i. And that comes out as negative 0.9505. What mode am I in? I'm in radian mode. If I were in degree mode, let's see what we would get. from that same entry, it would show up as negative 54.4623 and so on. So it gave me the angle as about negative 54.5 degrees. If I want, I can add 360 to that and get 305.5 degrees. And that is correct. We have a complex number that it is in quadrant 4, and so it gave us an angle that is in quadrant. Okay, now let's convert those others that we were looking at. You can do it the calculator way, or you can work it out yourself from the formulas. So 3 plus I, the r is the square root of 3 squared plus 1 squared, so the square root of 10. For the theta, the tangent of theta would be 1 over 3. That would be like the y over the x. So theta would be the arctangent of 1/3, which is around 18.4 degrees. That gives us an angle in quadrant 1, which is the quadrant where 3 plus I is. So that is the correct value of theta. We don't need to make any adjustments. So the trigonometric form is the square root of 10 times the cosine of 18.4 degrees plus I times the sine of 18.4 degrees. How about this one? Negative 2.3 plus 7.2i. Again, you could just use your calculator's conversion function, but if we're working it ourselves, r would be the square root of negative 2.3 squared plus 7.2 squared, and that comes out to be approximately 7.56. And the tangent of theta is the y over the x, 7.2 divided by negative 2.3. So if we just take the arctangent of that number, the calculator comes back with approximately negative 72.3 degrees. So an angle of negative 72.3 degrees is down here in quadrant 4. It would be equivalent to positive 287.7 degrees. But that's not what we want. We're dealing with a complex number in quadrant 2. So we don't want an angle that's down in quadrant 4, where the x's are positive and y's are negative. We want one up here in quadrant 2, where the x's are negative and the y's are positive, or the real parts are negative and the imaginary parts are positive. So how do we adjust for that? Simple, we take this 287.7 degrees, subtract 180, and that gives us 107.7 degrees. So that's the correct angle or argument. So the trigonometric form is approximately 7.56 times the cosine of 107.7 degrees plus I times the sine of 107.7 degrees. And these others, negative 4i. Now, the r would be the square root of 0 squared plus negative 4 squared. That would be the square root of 16, which is 4. And the theta, well, if you try to do tangent of theta equals negative 4 over 0, you get a division by 0 error. But I can see where that is. That's right straight down on the negative imaginary axis. That would be an angle of 270 degrees. So in trigonometric form, that's 4 times the cosine of 270 degrees plus I times the sine of 270 degrees. And the real number 2 is 2 times the cosine of 0 degrees plus I times the sine of 0 degrees. Hopefully you can just see that r, the distance from the origin, is 2, and that theta, the direction, is 0 degrees. Now, if we're going the other direction, from trigonometric form to a plus bi rectangular form, standard form, it's really just a matter of doing what it says. If you actually calculate the cosine and the sine of the angle, you get your real part and your imaginary part. So to convert 6 times the cosine of 120 degrees plus I times the sine of 120 degrees, the cosine of 120 degrees is negative 1/2. The sine of 120 degrees is the square root of 3 over 2. And so we get 6 times negative 1/2, which is negative 3, plus I times 6 times the square root of 3 over 2, which is 3 root 3. So the real part is 6 times the cosine of 120 degrees, it's negative 3. The imaginary part is 6 times the sine of 120 degrees, that's 3 times the square root of 3. And so we have negative 3 plus 3 root 3I. In decimal form, that's approximately negative 3 plus 5.2i. And watch me put this into the calculator. I could take advantage of some special conversion functions, but instead I'm just going to put it in pretty much just like this. 6 times the cosine of 120, and I am in degree mode, plus I times the sine of 120, and then close the big set of parentheses, hit enter, and it does show up as negative 3 plus approximately 5.2i. So if you put it into the calculator just like this, assuming you have the right kind of calculator, it will basically show it to you as the standard form of the complex number. Okay, another example, 3.7 times the cosine of 243 degrees plus I times the sine of 243 degrees. That just converts to approximately negative 1.68 minus 3.30i. And 1 times cosine pi plus I sine pi. Here the pi's mean I'm giving the angle in radians rather than degrees. No degree sign, notice. And the cosine of pi is, oops, I put that in the wrong place. It should have been here. Pretend the red dot is right here at an angle of pi. So the cosine of pi is negative 1, the sine of pi is 0, and we get 1 times negative 1 plus I times 0. That's really just negative 1. So I said it was supposed to be right here, negative 1 on the real axis. So in standard form, that is the number negative 1. Okay, we have some more things to talk about. I'll come back to that in part 3 and talk about when they're in trigonometric form, that makes complex numbers easy to multiply and divide and raise to powers. See you in part 3.